Okay, last example here in 7.3, example 3, and it does deal with that accumulated kind of money formula we talked about. A compound interest formula is really what it is, which is that the accumulated amount is equal to the principal times 1 plus the annual interest rate over the number of compounds per year to the power of the number of years times the compounds per year. And again, that formula is very useful. I do like pointing out that it is actually the general growth formula that we talked about before. The problem is that B is actually a bit of a pain to find. If you're getting 6.12% per year, then when you look at how much you're getting per quarter, you're getting a quarter as much. Now, the reason I like this formula so much is it's typically, or it has usually, the values given to you in a question. So it says Christina plans to buy a car. She saved $5,000. So that's how much she has today. She needs to make sure that she invests her money for a long enough time so that it accumulates to 5,900. Well, she knows that she can put it into some kind of a term deposit, whatever that is, and the annual interest rate, or R. Now, here's really an important concept, that the interest rate is 6.12% per year, but as a decimal number, R is 0.0612. And I always like reminding students that this percent symbol literally means per 100, and per represents division. So that's 6.12 divided by 100, which is 0.0612. Percents have become just kind of how we talk in everyday society. Mathematically, decimals are better. And I say that as a math teacher, so a little bit biased for sure. It says that it's compounded quarterly, and I always recommend students that get a little stuck with this is how many quarters in a dollar? There's the same amount of quarters in a year. So that would be 4 compounds per year, 1 each quarter. And then, annoyingly in this question, it says, how long until she has enough money to buy a car? Now, the one thing that I do like to point out is that she only gets interests at the end of each quarter. So I'm just going to put in a bracket that we have to round up to the nearest quarter. And really what I'm saying with that is if we solve this and I get that, T is equal to, let's just say 4.1, well, she is going to get a compound at 4, then at 4.25 years, then at 4.5 years, 4.75 years. So 4.1 years isn't actually a solution because she hasn't gotten any interest, a tenth of the way through the year. That is a tricky concept for a lot of students. What I would encourage you is if you do have, a bank account, which I'm sure grade 12s you do, take a look at when you actually get paid your interest. And it's always, the last day of the month. You don't actually have that interest until the very end. Now, one of the things, if you carry on with math and you go into calculus, we talk about continuous exponential growth, which is a great way to model very large populations. That's not what this is. This is discrete exponential growth that's happening every quarter, so our answer can only be in quarters of years. Now, what some students will do is instead of this t times n, they will use an x, where x would be the number of quarters. And I don't mind that, but I would much rather, because it says, it gives the annual interest per year and stuff like that, I like to keep this in the unit that they give us. All right, now this is a tricky question because we're going to put these numbers in and it's going to appear like we hit a bit of a brick wall. So 5,900 is equal to 5,000 times 1 plus 0.0612 divided by 4 to the power of t times 4. And we run into a problem because our variable's in the exponent. And the reality is that right now, we do not have the algebraic technique for solving this. So we are going to have to use a graphical technique, which not all students love to do, but it is nice. And at least you get to use your calculator for it. Now I'm going to clean this up just a little bit first and get 5,900 is equal to 5,000 times 1.0153 all to the power of 4t. Really important that what I did here is I divided by 4 first, and then I added that to 1. Now, that being said, you can plug into your calculator 1 plus 0.0612 divided by 4, and it will give you that number, 1.0153. And, talking about exponential functions and what that number actually is, that number tells me that I gain 1.53% of my money, so I have 101.53% of what I invested at the end of one quarter. And then I'm going to get 101.53% of what I had at that quarter in the next quarter. And what happens is we start getting interest on the interest, and compound interest grows quite quickly in maybe not the right conditions, but when we talk about, $5,000 isn't a lot, but what if that's $500,000? all of a sudden, there are people out there that live off interest of very, probably large family fortunes and stuff. So probably not a realistic, career plan for us. But when we do talk about looking at exponential growth, I really can't understate how quickly it can happen and how very, very large your values can become. All right, we're going to solve this with our calculator. So grab that again. And we need to type our functions in. So I'm going to go back to my y equals and get rid of example 2 there. And I'm just going to put in the left side of the equation, which was 5,900, and the right side of the equation, which was 5,000 times 1.0153 to the power of, and in our friendly bracket, we have to put 4x. Right? Putting 4t, the calculator will recognize t as a stored number. It will not graph anything. Now, the nice thing about compound interest formulas is it gives us a lot more context for the question, and we can determine some of our window settings without actually looking at, values or anything like that. I can invest for negative time. So x min is going to be 0. Keep in mind that x is the number of years. I'm hoping that Christina doesn't have to save for more than 20 years to buy this car. Y is the amount of money in the account. So 0. They're never going to take money out of the account. And really importantly, we only really care about what happens until we get to 5,900, and then we're done. So I'm going to make my Y max 10,000, just so we can see a wide range of values. And when we graph, sorry about that, I hit the wrong button there. So when we graph that, what we see happening is there's Y1, the left-hand side is just Y equals 5,900, and there's my 5,000 times 1.0153 to the power of 4x. Doesn't look like it's growing very quickly, but remember that Christina's not doing anything here. That money's just sitting in a bank account. And I'd like to point out that if we let this money just kind of sit there for 5 years, I'm on the wrong function. This is not my day for using that trace. If I let this sit for 5 years, she made, $1,700 for not doing anything. And this is a pretty important concept. And I don't want to, philosophize to you guys too much, but you should invest money now, because the longer it sits there, the more interest on interest you get, and then the more money you get to play with at the end. Now, what we're concerned about is the intersection point. So I'm going to solve that with second trace number 5, the intersect. And like I've done before, and you've seen me do before, I'm going to put my cursor on the intersect and hit enter 3 times. And it tells me that it occurs at 2.725. Now, it is very important that I don't actually get that money at that point. So what I'm going to do to show you how this growth works is I'm going to go in my table setup, and I'm going to put my independent on ask. And the reason I want to do that is I want to show you what happens during that second year. So at the end of my second year quarter, I have 5,645. Then when we're 1 quarter into year 2, I have 5,732. When we're halfway through year 2, I have 5,819. Then at 2.75, all of a sudden I have 5,908. So Christina has an extra $8. It's really important that our calculator graphs continuous functions. This isn't that. X can only be quarters of years because we're not getting the interest in between. And just to maybe finish that year, we see that after 3 years of investing our money, we got $6,000. So we made, an extra 20% of our money just by leaving it there. I mean, 3 years is a long time, but if you have the self-discipline to do this, you definitely should, because it is a huge, huge advantage to know exactly what your money is doing when you invest it. All right, so I got a solution, and I want to write this down so we can make that connection, that we got T was equal to 2.725, blah, 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 but we're going to round up. So it happens at 2.75 years. Now, depending on the question may ask you, how many quarters or weeks or whatever it is, doesn't matter. I would recommend you think of that as just kind of an old school unit conversion. What compounding quarterly really is that there are 4 quarters in 1 year. And if I multiply this across, what's going to happen is that my years are going to cancel, and I'm going to end up with 8 plus 3, so 11 quarters. Now, you do have to be a little careful. I'm not talking about the money, the quarters. I'm talking about 11 quarters of the year until Christina has enough cash saved up to buy, her dream car or whatever that is. All right, I'm going to put up that assignment page here. I can find it, and then I'm just going to write, I'm going to leave it there for a second. I want to write some kind of exponent laws that you are going to run into throughout here. When you're multiplying common bases, you add their exponents. When you are dividing common bases, you subtract their exponents. If we have an exponent on an exponent, we multiply those. And then the other really important one is that if we have a fractional exponent, that becomes the index of our radical. And this last one actually has another form that we typically see. If you have x to the power of n over m, a fraction, you can write this as the mth root of x to the power of n. And the last one that I always bring up, it may come up for sure, is if you have a negative exponent, that is 1 over the positive exponent that you had, or the positive version of the negative. Sorry, I said that in a really bad way. Make sure you are trying these questions. Yeah, good luck, and email me if you are struggling at all, and I will help you work through it as much as I possibly can.